Yeah, thanks. So here, in this BLP approach, the utility is indexed by individuals, choices, and markets, where sort of in different markets, the characteristics of a choice may change. And so in particular, that is very important for prices that are allowed to. So at some level, you kind of wonder what a choice is if it changes its characteristics, but obviously for price, you could still have exactly the same object, but have a different price in different markets. The Zeta JT here is an unobserved product characteristic. And so there it's important that they allow that to vary both by market and by product. And then there's epsilon IJT that has an extreme value distribution that sort of has this logit form that's going to be independent across individuals, products, and markets. And I'll talk a little bit later about sort of the role of that and sort of why it is extremely useful to have that in there. Then for the individual level coefficients, they specify those to follow a normal distribution centered at Ci prime gamma plus the average value of the coefficients. So just the same as in the random effect specification we used before. And so here, what are the data that they're going to need? They don't necessarily need individual level choice data. Need market shares for all these choices, proportions of these choices in each market. You need observations from the marginal distribution of the individual characteristics from each market. Now, then, what do they do? And so you're going to spend a couple of minutes sort of going through this. That may to at least give you some flavor of the way this works. So you can think of the utility as consisting of two parts. One, the part that is choice and market specific, and then all the rest that is indexed by the individual, by I, and it's independent of the rest that is centered at zero, given in a particular market for a particular choice. So the first part is this, what is written here as delta JT, that consists of the systematic part of the choice characteristics, beta prime xJT, plus the unobserved choice market-specific component, zeta JT. And so the epsilon IT is in the remaining part, as well as the random part of the individual preferences, the Ci prime gamma plus eta I, but the CIs are normalized to a mean zero. So now, how do you go about estimating this? Suppose we know all these parameters. So we know gamma, sigma, and we know the delta JTs. Then we can figure out. What that would imply for the market share for a particular product. How could you do that? Well, if I tell you what gamma, sigma, and the delta JTs are, you could just simulate for a bunch of individuals what their utility would be under each choice. You can see which one is the highest utility. You can figure out what choice individuals would make. And you can figure out what choice individuals would make on average. You can figure out what the market share is in a particular market. So if I tell you sort of both gamma, I tell you sigma, so you can draw the eta I's. I tell you what delta JT is, so you know the systematic part of the utility. You can just simulate the unobserved parts of the utility, and you can figure out what the market share is for a particular choice in a particular market. And so the implication of that is that you can write the market share for a particular product as a function of these three objects, delta, JT, gamma, and sigma. Now, in a very simple case, if I actually fixed gamma at 0 and sigma at 0, the market share would be very simple. It would just be the ratio of these e to the power delta JTs. But no matter what the values are for gamma and sigma, you can in principle simulate this. Sort of be messy. It may take a while, but it's sort of only computer time. You could, in principle, there would be a straightforward way of estimating what the market share would be given the values of these parameters. And so you would get this implicit function of the market shares implied by values of delta, gamma, and sigma. Then the next step is to fix only the last two parts, the gamma and the sigma, and now look at that function and try to figure out for what values of delta you actually match the implied market share to the observed market share. And so kind of just counting, we have exactly one delta JT for each market share, so you sort of have equal the same number of parameters as equations you're trying to fix. In fact, from the structure of this problem, it's a very well-defined problem, and you're always going to be able to find a set of delta JTs that fit exactly the market shares. Because in principle, these delta JTs just tell you how attractive they tell you the systematic part of the attractiveness of a particular choice, and if you make that go up, you can make the market share go up, and you can do that in a way that you balance all the market shares. And sort of in BLP, they suggest a particular way of doing that, but sort of in principle, that's going to be a very straightforward problem to solve. Then the last part, and that's really the part that's the most difficult. Now, this is all for particular values of gamma and sigma, but we're actually trying to figure out what these values are. And so what we said so far is that irrespective of the values of gamma and sigma, you can figure out a set of deltas that fits the market shares. But now, not only do we want to find a set of deltas that fits the market share, we want to find a set of deltas such that the difference between delta and beta prime xt, beta prime xjt, is uncorrelated with a bunch of other things. And that's sort of where this is going to be really challenging, and where computationally this is very demanding. But at least in principle, people have used this a fair amount of and gotten it to work. Now, there's a whole bunch of references in the notes, sort of about discussions of how to make this work. Some stuff by Aviv Niveau that's very readable and accessible. Now, let me just kind of, as a final illustration of this part, suppose we actually were in a case where we had a conditional loaded model and we were doing this. I suppose we actually fixed gamma and sigma at 0, so we did impose the conditional loaded conditions. Then what this is doing essentially is taking these market shares, looking at the relative difference, sort of the difference in the logs for these market shares, and looking at the difference between that and beta prime xjt, and given some set of instruments, you would essentially be doing two Slazely squares on these transformations of the market shares. And the thing that makes this much more complicated is that before doing that, the instrumental variables part, you allow for these random coefficients and these individual specific marginal utilities, and that's the part that makes this very challenging to do with these aggregate data. Now, going back a second, so with this specification alone, if you actually had individual level data using Gibbs sampling and these Markov chain Monte Carlo methods, would actually be extremely straightforward. It would still, it would be conceptually straightforward. It would be fairly easy to implement, and it would likely work much faster than these numerical methods that use only aggregate data. So even though it's obviously extremely useful to be able to do this only with aggregate data, there clearly is a considerable price to pay in terms of implementation as well as in terms of precision. Okay, and sort of this sort of partly relates to the next thing where I want to talk a little bit about allowing for multiple unobserved choice characteristics. So because the Berry, Levinson, and Pecos uses only aggregate data, it's very important for them that it's just a single unobserved choice characteristic, because they need to feed it through this the single observation for each market, namely the market share. If you actually have if you have individual level data and variation in the choice characteristics, you can allow for more than one unobserved choice characteristic. So there've been a bunch of papers doing that, including Elrod and Keene and Gatler and Shachar, who actually allow for more than two unobserved choice characteristics. In some sense, you can think of this as of these unobserved choice characteristics as freeing up the covariance matrix in the multinomial probit setting. By having an unobserved choice characteristic, you're allowing for one additional free parameter in that covariance matrix, but you're not immediately freeing the whole thing up completely. And so here, this is kind of described in more detail in some of the work in this paper I did with Susan. You can think another way of thinking about the multinomial probit model is that it implicitly allows for as many unobserved choice characteristics as there are choices, and so that sort of at one level makes it obviously extremely flexible, but on the other side it makes it clearly frees up way more than the data could ever tell you, and so the formal result in this paper with Susan is that in fact, irrespective of what the data look like, you can always explain the choices in a way consistent with utility maximization by just having two unobserved product characteristics. So partly that is showing that having this completely unrestricted covariance matrix relies very heavily on the functional form for identification, and that sort of in a non-parametric sense, you couldn't possibly identify that whole covariance matrix. Now, so the way we set things up in that paper is sort of very similar to these random effects or these BLP models. We allow the utility to depend on the choice characteristics. So this should obviously be a JT rather than IT. There's choice-specific characteristics. Then there's potentially up to two unobserved choice characteristics, zeta J, as well as a idiosyncratic error epsilon I JT. Now, once you allow for more than one unobserved choice characteristic, the likelihood function is going to be extremely awkward to deal with again. It's certainly going to have multiple modes. It's going to be very difficult to even evaluate it. But these Bayesian numerical methods are very patient, they're very convenient for this kind of thing, and they allow you to do this sort of by breaking it up into a whole bunch of essentially normal linear model steps. It's relatively straightforward to do that. Okay, so the final set of comments I want to make about hedonic models, where so recently a number of people have also looked at models that only sort of model the utility only as a function of the characteristics. It's essentially getting rid of the epsilon ijt here, which at some level is sort of a bit of an awkward component to have there. So that you'd think that the utility for a particular choice should in the end depend on the characteristics of that choice and should depend on individual characteristics. You may not observe all of these, but there's sort of no reason to have a component that just varies randomly across all choices and across individuals. And so in this literature, people have tried to use only observed and unobserved choice characteristics, so they have a relatively small number of them, instead of the sort of this multinomial probit version where you have as many unobserved product characteristics as choices in the end. And so to see if you could rationalize the data that way and estimate these models. And so I'm going to make two arguments here why you actually do want to have this epsilon ij in there if you want to take these models to the data. And so the main point is, so there's 2 points to that. One is that not having these epsilon ij's in there makes these models extremely sensitive to measurement error. Suppose, in fact, these models that you have choice data that were generated by one of these hedonic or pure characteristic models, then it's possible, so one of the attractions of these models is that they can actually predict zero market share for some products. If a product has characteristics that are dominated by some other choice, if there is an epsilon ij in there, it would imply that there was still some market share for this choice with dominated characteristics, but without this epsilon ij, the model could actually imply that a particular choice has zero market share. Now, suppose that the data were generated by this model, but suppose there was a single unit for whom we observed that choice due to some measurement error. Then the results would be extremely sensitive to that, irrespective of how many observations you have. This single mismeasured observation would force the parameters to be away from the values that generated all the other values. And so that's sort of very unusual characteristic. Typically, you think of econometric models that are well behaved, that if there's some contamination, that if some part of the data was not generated by the same joint distribution as the others, if the fraction of the data that were the fraction of contaminated data was small enough, then you would get back to estimating the parameters consistently. Here, that would not be the case. Irrespective of how many observations you have that were generated by the Hedonic model, the parameters would always be substantially away from the true values, even with a single mismeasured variable. And so clearly it would be nice to make these models more robust, and you could kind of think of just doing that directly. We're saying, well, suppose that in fact the underlying choice was based on this pure characteristics model, but there was some measurement error. And you could do this sort of in a couple of different ways. One way is to just say, if there's measurement error, you would get one of the other choices. You would observe one of the other choices randomly chosen from the overall set of choices. Alternative would be to just add this epsilon ij to the utility function, and that would imply that you would be more likely to see a close to optimal choice if the choice was mismeasured than one that is far away from the optimal one. So the first argument is that by having the epsilon ij in there, you would essentially allow for measurement error in the pure characteristic model. Second part is that in the end, the model with the epsilon ij essentially nests the pure characteristics model. Even though you fix the variance for the epsilon ij by having it be extreme value, if the data were generated by the pure characteristics model, you can rescale the systematic part of the utility function in a way that the choice probabilities from the model with the epsilon ij would be arbitrarily close to the choice probabilities coming from the pure characteristics model. So to point where that even if the data come from a pure characteristics model, you wouldn't lose much by having this additional term, because you would essentially be nesting that. And the big advantage would be that you would make things much more robust, and that's going to be advantageous both computationally as well as in the end for interpreting the parameters. All right, this is it for this lecture. Any questions here? Yeah.
So one important question we would want to answer with a discrete choice model is what happens when we introduce a new good. So you mentioned, for example, with the random coefficients model that if there's a new good, it needs to be the case that it has characteristics similar to the observed characteristics that you already see in the data. With the newer models, the DLP model and the newer model of Susan that has unobserved product characteristics, what happens if we have a new good that either has characteristics that are completely different from characteristics of new existing goods, or the value of the characteristics that's entirely out of the range of the data?
Yeah, so in those, yeah.
How do you keep the unobserved characteristics?
But it's in these models with, so going back to the conditional logit models, there the implications for the introduction of new goods are typically very unattractive, that you would potentially get very large market shares for new products, even if they were very close to existing ones. These random effects models tend to generate much more realistic predictions for these new goods. Once you allow for these models with either unobserved product characteristics, but also these multinomial probit models, you have to make a lot more choices in order to predict the market share for a new product. In these models with unobserved choice characteristics, you need to assume either postulate the values for the unobserved choice characteristic, or you need to you can do this for different values, and you can sort of get a whole range of predictions. But sort of once you allow for the possibility of there being unobserved choice characteristics, it's clearly difficult to predict very precisely what the market share for a new product is going to be. But in some sense, that's clearly very realistic. In a lot of cases, you're not going to be able to predict very precisely what new goods are going to do. And this gives you, for these models, by using the distribution of unobserved choice characteristics that you see, you can actually get a much more realistic range of market shares for these for the new goods than you would get under, say, the conditional logit model. Okay, thanks.